So
I just wasn't sure on how to start it because the cosine n is not like n to the pi, so I wasn't sure if we'd be able to like make it the negative one alternating.
gotcha. So number 16, this is page 738. And the big idea with section 11.6 was the idea of absolute convergence, right? And that's going to come into play here because, like you pointed out, this isn't, you said it's not cosine of n pi, right? Which would be a little more direct. What did we learn last time about cosine n pi?
Substitute negative 1 to the...
Yeah, effectively acts like negative 1 to the n, or negative 1 to the n plus 1. Yeah, depending on where it starts. So there's certain formats of problems that kind of tell you what to try. Do you guys see what he's thinking about, though? The cosine is oscillatory, right? So it does change sign, but fundamentally it's kind of like a constant compared to something else, right? We kind of looked at it that way before. What's the bottom look like, and what's it trying to be? What's extra on the bottom? So do you see the extra pieces here that might tell me what I want to do with this? Yeah, what's the power on the bottom? 2/3. And the top is effectively what? The top is effectively what kind of thing? So like a constant, roughly, right? It's somewhat alternating in some weird pattern. Hey, all right. So you start to look at what seems to be extra that I could strip away by using either... So you could either do that process where you can either take it away. What would that be? Direct comparison. Cool. Or what's the thing we learned right after that that's sometimes, or very often, much better, but sometimes not so good? Limit comparison. I love it. So it's the same idea as before. You look at it. You got to get used to the fact that these are kind of extraneous in a way. You want to look at really what is this trying to be. And this section gives it away a little bit because of the fact that it alternates weirdly. What do I really want to do to this so I can see what's happening? I want to, it's negative sometimes, positive sometimes. Yeah, I want to look at absolute values. I want to look for absolute convergence, right? Okay, so first thing I could do would be to do what? What could I do with this? All right, I could try to rewrite this, right? So if I want to do direct comparison, that would enable me to strip away those extra pieces, right? So how could I, so here's my AN that I'm working with.
And from the P series, we think that it's going to diverge, so we would need a floor.
Exactly. Now the first thing I want to do, though, you got to be careful. What is true about direct comparison tests? What must be true about the sequence elements I'm looking at? I don't know if you guys remember. They have to be positive. So since we're looking for absolute convergence, we can just go ahead and look at the absolute value of those sequence elements, right? So if I can show that that converges, what must be true about this?
Absolutely.
Yeah, why, if that converges, why must this converge?
Because it makes it easier if it's...
Beautiful, because some of these are negative, some of them are positive, so they're going to be subtracting, right? Now, we kind of already know, we already kind of know that this is going to do what? Diverge, because this is trying to be P-series. I love it. So if we look at this, let's just work with this directly. Let's see if you can do this. So you could either attack this with direct comparison. You could attack this with a limit comparison, right? So if I wanted to do limit comparison, what would I use? What is it? Why do we think this is going to diverge? Because it's trying to be fundamentally what? What's my BN going to be?
1 over n to the 2/3.
I like it. So that's what it's trying to be. So this is the way that we figure out if it's going to converge or diverge, because that guides us as to what we're going to do next. And that process of figuring it out very often actually gives us our other sequence to compare to. Right? So the series that this represents would diverge. So how do I do the limit comparison test? What's that all about? Yeah, so if I look at the limit, and again, if you want to, you get that quick reference now, right? It's down halfway down the page. So for the limit comparison, I want to set up the limit. How do I set this up? All right, n goes to infinity. An over bn, I like it. So what have we figured out now, finally, after doing some of these? I just want to put an, and then I can put the reciprocal of bn next to it. Good. So I get 3 minus cosine n over n 2/3 minus 2. Divided by that, so times that. Okay. And then what can you do with that? Why does this look a little different than what we were doing before? What's still kind of like in our way? Cosine. I like it. So let's look at this here. What can I do with this here? Well, be careful. Don't get too optimistic. Right? You can at least distribute it, yeah. Yeah, I could have just left it outside, right? Because what's 3 minus cosine n? What's the absolute value of 3 minus cosine n? What is that fundamentally? I don't want to look for a number answer because you can't give that to me, but it's what kind of thing? It's constant. What kind of constant? It's a positive constant, right? Because we took the absolute value of it. So what I really have here then is n to the 2/3. Oh boy. I love it when they do that. So what I really have here is constant times n to the 2/3 over n to the 2/3 minus 2.
N to the 2/3 over n to the 2/3 use a ratio.
All right. So, I mean, what would this be? If this was just a 5, what would this be? If this was a 5 n to the 2/3? Yeah, exactly. Right? So gave the here. Well, we already have the, yeah, okay. And what does that do? Does it diverges for what reason?
Because it never approaches a single number.
Yeah, that cosine n is still doing that oscillation thing, right? So we saw something like this before when we tried the limit comparison test.
Inconclusive.
Use a different test.
Yeah, we might want to use a different test. So we can see what's really going on here. So we could do the first thing we were thinking about, the direct comparison test, right? We could do it that way. Okay, maybe. Yeah. But if you try to do the direct comparison test, what are you going to try to do? If you think this thing diverges, what do you want to find?
More.
Good, a floor. You want to find something that's smaller than it that will push it to infinity, right? So, for example, that means that if you want to make it smaller, could I just take that minus 2 away? Yeah, because then you're making the bottom bigger. That makes the whole thing smaller. And then on the top, what can I do with that 3? If I took that away, is it smaller? Yeah, good. All right. Cool. So that worked a little bit better. Now I'm trying to think about why I did the limit comparison. So if you just look at that by itself, if you look at this sequence here, you can say that this, so what do you guys just tell me? That's less than what? Yeah, so doing one thing at a time is less than negative cosine over, I'm sorry, greater than. So we're trying to find a floor. We want something that's smaller than ours that diverges. So it's definitely, this is bigger than taking a 3 away from the top. And then it's also bigger than, good, because that makes our inequality go the way that we want it to. And what does this thing do? And let's go one more step. This is going to be bigger than what?
Could you put a 1 in for cosine, so as big as it goes?
Yeah, but remember, we're trying to make this guy smaller than this, right? So here's where we're doing a little adjustment. So the very first thing we did was you did 3 minus, and we took the 3 away. Cool? Now looking back, now there's, all I could really do here is to put like a 0 there, right? I'm trying to make the result here smaller. So if I put a 1 there, that's actually making the result bigger most of the time, right? So if I back up just a little bit, be a little more careful right at this step, I don't have to push myself into that corner. But you can see the problem I got here. If I wanted this to go the other way, then I could just replace that with 1, and the inequality would be true, right? So I can go back up here and be a little more careful with that 3 that we did up here. So maybe we want to go the other way with this. What is this definitely bigger than? Since this is 3 minus cosine, what's the smallest this top could be? 2, right? So how do I make something that's always smaller than this then? I can put a what up top?
Less than 2.
Let me stop right there. Does everybody see when we get a 2 here? What's the absolute smallest this can currently be? Is 2.
Yeah.
So if I want to make something that's even smaller, what can I put on top? 1. Cool. So me getting rid of that 3 turns out not to be good because it left that cosine behind, which is a big problem. And now I can do, what can I do next?
You plug off the 2.
Plug off the 2.
Series. And that.
Since this does what?
Divergence.
Yeah, good. Divergent P series
You say it's conditionally.
is 2/3 less than 1.
Or, would we still have to do like an alternating test to see if it's conditionally convergent, or?
Could you apply the alternating series test to this?
I don't think so.
Why not?
Because it's a weird alternation.
Exactly. It's a irregular alternation,
Okay.
right? So the best you can do with this is test for absolute convergence. So right here we can say this is at least definitely not absolutely convergent. Right, because it's basically a P series where P is 2/3. And what's the
Sorry.
what's the limit as n goes to infinity of this? Yeah, it's definitely going to be 0 even with that alternation up here. So that's why thankfully, that's why we did all this. Because it could be convergent if the limit is 0. But you can't really tease out that alternation because it's an irregular alternation. So you can't, it's just not -1 to the n plus 1 or something like that. Okay, so anything else from homework yet?
That same page, but number 20.
From what side?
So what's one way I can rewrite this? This is a little bit simpler than the last one. What's one way I can rewrite this to see the AN a little better? Yeah, how can I break this up here? Well, I want to kind of tease that negative part out. All right, so it'd be -1 to the n, 2 to the n, over n to the n. So, if I want to test this for conditional convergence, at least, if I want to test this to see if it's conditionally convergent, so I don't want to do absolute convergence. What do I need to show? Yeah, so remember, the nice thing is there's two things I need to show. The nice thing is alternating series, so what does that require us to do? So you got your little cheat sheet if you want, or do you remember? Decreasing. And the limit must be 0. I like it. So how do you show that this is, now this one's really kind of gruesome if you want to try to show this correctly. And because you have this end to the end part on the bottom, right? So one way we can kind of take care of that is to do it the other way. How else can I show it's decreasing? So this is my AN. My AN, what is my AN, by the way? What is that by itself? All right.
Because you get like A1 compared to A2.
Well, be less specific.
Or AN to AN.
Yeah, so if I look at AN plus 1, if it's decreasing, what must be true about how that relates to AN? If it's decreasing, the next term has to be, that would be increasing, right? If it's decreasing, the next term should be smaller. Good. So what is the next term then? AN is right there.
Has to be equal to N plus 1 over N plus 1. N plus 1.
Good. N plus 1 to the N plus 1. So now, what's nice about this is if I kind of start with this side here, 2 to the n plus 1 over n plus 1 to the n plus 1. What's definitely true about that bottom compared to my other bottom? Yeah, so I want to make this bigger, and I want to make it look like this eventually. So definitely, if I replace this bottom with that, how does that relate? Will it get bigger or smaller? Is this bigger than that?
Yeah.
Yes. So if I replace this with that, the whole thing is going to get
Smaller,
bigger, because I'll be dividing by less. You guys, we've seen that happen a lot of times, especially direct comparison tests. So this is definitely true here. And of course on the top, what do I have? Truly, we're better with this now. The 2 to the n plus 1, what can I do with that?
Split it up.
Split it up, I love it. So that would be,
2 to the n times 2 to the 2.
and of course if I want to make this bigger,
Like terms?
Because if I just take that 2 away, what happens? It gets smaller, right? And I want to compare these two things here. So let's try another tact. This is not going to go the way I want it to go here for the inequalities, right? Yeah. What's up?
To the end is the smaller than.
No. So I need it to be this on that next side, not just something that looks like that.
Like terms multiplied by 2.
So another way to kind of do this step here is to subtract this and show that it's negative. Right, so another way you could try to do it. Let's see. So one thing I could do there is, what can I do on the top here?
The cross multiply. These like terms in the
We
bottom.
can't. Well, I don't necessarily want to get these together. Right? I'm going to quickly face the same problem I've got currently, which is if I take a 2 to the n out, I get there, except I need a 2 there. That's my bad. There's one more 2 there, so I leave 1, 2 there. And then I got to show that that thing there is negative somehow. Now, from the very beginning, real quick, right here, what does this look like here? How can I rewrite this statement there? Yeah. So that almost looks like what kind of thing? And n, of course, is going to quickly be how related to 2. So another way to break this down is, if I can show that this is decreasing and less than 1, then obviously the nth power of it must be decreasing, much like the whole idea behind a geometric series. So if I let for all n's past what number, of course, how do I get past 1? I've got to start at 3. For n greater than or equal to 3, this of course is less than 1. So then 2 over n to the n, much like a geometric series, is going to have to be decreasing. I'm going to be multiplying over and over by a number smaller than 1. So this is definitely going to be decreasing. Okay, so then we tried every way we know how to show that this thing was decreasing. And why do we want to show it's decreasing? What are we trying to use here? Alternating series. Cool. So we got it's decreasing. Is the limit 0?
Yes. Yeah.
Hell yeah. Right. So if you have a limit and it goes to infinity of this business here, now if you really, really wanted to show it fully technically, does anybody remember how you could do that? What's really bad about this limit? Why is it a little weird? Well, it's not. It's going to be like 0 to the infinity. Now, you guys remember how to take care of that power? Yes, exactly. So what I do is I say, okay, I'm looking at this guy here. If I take ln of both sides, we might as well make this real values here. Well, let's see what we need to do. And then I can do the limit here. Now, what do you think I'm going to want to do here eventually? Because what is it currently? What's happening? If I let n go to infinity, what do I have happening here?
This in front of the,
Infinity times zero is
they change the
infinity
volume.
times is one.
Seems like we want the
Yeah, if when I'm going to infinity inside here, what's happening?
zero.
Just go to zero.
0. Natural log of 0 is... No, natural log of 1 is 0, right? So what's the natural log of 0?
Negative infinity.
Yeah. So that is really, really freaky. And natural log of 2.
Instead of doing alternating, could we do the ratio test?
We're not, this is before that section though. Be careful. Is it? This is from what section?
11.6.
Oh, yeah, we're in this ratio and root section.
You just
Oh.
take the root test.
Man, that's my bad entirely. I thought it was way worse than that. I thought we were in a section before. All right. So that's an excellent idea. Let's try that. I think I pointed out this specific problem last time, and then I just forgot that I did that. I thought we were back in that previous section where we couldn't use root and ratio tests. Yeah, the Ruscio, right? Ruscio test. So why would you use? Obviously, you want to use what here? Root test. And why do I want to use root test here? Now that I realize you can't, because everything's raised to the nth power. So what exactly does the root test look like just in general? What do I put here? Nth root of absolute value of an. Good. I took us on a wild trip. That's because I didn't think we could use that yet. And you see how freaky it gets without being able to use that root test. But this is a beautiful candidate for the root test. So absolute value of an just does what to this? It just makes it what we're using before, exactly. N to the n. So of course, now watch this. This is awesome. I just love that I just did that. So the nth root of 2 to the n over n to the n. And of course, what happens there? 2 over n, which is 0, which is more specifically what's important for the root test. That is, what's the result of the root test got to be? You want to compare it to 1. Yeah, you want to compare it to 1, so that's less than 1. Which means what? Beautiful. All right. Look how short that was.
That was good practice.
Sure. So if I would have given that problem before this section, that would have been remarkably difficult. All right, you could see the evidence of it from what we just went through. So it's my bad. I didn't realize we were in the section where we could use the root test. I'm like, damn. The thing I put down on the little cheat sheet, the little quick reference sheet, and I really want you guys to understand this because I didn't understand it until I actually taught this, is that L from the result, in the proof we saw this, L acts just like R from a geometric series. So that makes it easier to remember the results. What's got to be true about our geometric series R for it to converge? R has to be less than 1. And L in this case, you saw it from the proof, acts like an R. So it makes it very easy to remember this, which you must do. You got to remember what you're looking for. But the root test, ratio test, both times you're looking for what? Less than 1. That would tell you it is absolutely convergent. If it's greater than 1, divergent. If it equals 1, who knows? We got to figure out something else. Yeah. Okay. All right, so thank God that root test exists. If I would have just figured out sooner I could use it, that would have been really, really good. Anything else from homework before we get into...
Can you just derive the AN and 28 on the same section?
Where are we at, sir?
11.6. 28.
Number 28. Oh yeah, so this one they try to give you a hint. I'll get you started on this one. So 28, every now and again they're going to give you something that's written not in summation notation. So they're just trying to keep that skill alive, how to rewrite this in that notation. Now, let me keep going from there. What does this feel like it might be related to? What's kind of happening here? Am I multiplying by the same thing over and over? No. What? What does this feel like it's related to? What function? See, not really, because geometric requires that what you're multiplying by has to be the same. That's why you can identify it as R. I can't use a single R here. What I'm multiplying by is continuously changing. But I am multiplying by what does that look like? Like, what are you saying, Andrew? Are you drawing in the air?
A little exponent guy?
Yes, cool. What is that? Exponent. What do we call it? We don't call it punctuation. What do we call it? What's this do? Factorial. It's just one thing that throws you off in this problem is if they would have written the bottom in reverse order, that might have helped. I don't know, because what are we used to with factorial? What's 7 factorial?
7 times 6.
All right, now don't get too happy, because you still got to work out how the hell this is. But it's not too evil, because what do you keep multiplying by, it looks like? First you have 5, and then you multiply by something that is 3 more, and then 3 more. And on the top, you're really doing... Now, what's happening on the top? Let's look at the next element here, because the top looks a little bit more interesting. No, that's fine. Okay, cool. Same idea, just a different number. Okay. So now that you know it's fundamentally a factorial, and do you see now, if you saw that on another problem, you'd be able to identify it. Factorial, basically, every problem is going to have more and more products, kind of all based on the same idea, right? So if I want 5 and then 5 times 8, I know it's going to have what inside? So you get from 5 to 8 to 11?
3.
Yeah. And I know I want the first term to be 5 alone. So how many 3's do I want to add on the first 5? 0. Right? So what do I want next to the 3? The 3 is what I keep. So you start at 5. 5 plus 3 would be 8. 5 plus 6 would be 11, right? And since we really have control over this bad boy, what do we want to start n at to make this a little bit easier? I want to start it at 0. Do you guys see why? Because the first, second, third element, the third element,
It's basically 3 times 6.
yeah, so the first element I want it just to be 5. So if n is 0, I don't want any 3's. Then I want one more 3. Now, of course, what's after this? What I have not put it there yet that we know has got to be there? Factorial. So what's got to the 3 is I had 1 3, I had 2 3's, I had 3 3's. So what's got to go next to the 3? N. 11. Now, I'll do that part. You guys do the top part. It's very similar. Cool. And once you got it written down, what test do you think you're going to use? What's good for factorials? Ratio test. I like it. Because I think there's same instructions here on this one. Yeah. Do you guys get a feel for that? Now that we've seen factorials working, they are going to put more complicated expressions of factorial in there for us to work with. All right. So let's do this. I didn't mind going a little bit further with questions because it's all good review. If you have a book, I'm going to look at page 741. Actually, I'm sorry. I think I decided to go to the review section. Page 779. So you can work together. You can work alone, however you like. I know some of you guys like to work together. Some of you are lone wolves. That's all right. So if you're looking at page 779, let's see. Basically 12 through 19. It's pretty good right there. So 12 through 19. So this could be anything. This could be, what do you want to try first? If it's not obvious, like if you look at it, you just know it's geometric. You can just attack it that way. But if you're not sure, what do you try first? Yeah, you want to see if there's a reason to do anything. Yeah, maybe it diverges right off the bat, so you don't have to worry about it. So if the sequence diverges, the series has no chance. Right, but be careful. If the sequence limit is 0, what does that mean? Yeah, that means you got to do more work. The series has a chance to converge.